So let's get started. So first of all, let's talk about the paper presentation, because last time we did not really go through the rule and then what you need to do for the paper presentation. So for the paper presentation, we'll do it every Friday. So you need to join the link and to do the presentation. But if you are not a presenter, you do not need to join. But if you're going to learn about some papers from others, you can still join with us. So what do we expect for the presentations? Actually, it takes about 10 to 12 minutes. So it includes the four main parts. First of all, it's a background and the trend. So it takes about 2 minutes because we only have 10 to 12 minutes, so it doesn't need to be too long. But it needs to include some very essential part for the paper. So you can think about like what kind of background is the necessary one. If you do not really include this background, maybe the audience cannot really understand what the paper is about. So it should be in the background. And then the following on will be the related works and observation and motivation. So it takes around 3 to 4 minutes, depends. So usually you need to think about like, what's the key related works in this paper? So for example, in this paper, we'll say like, hey, there are some prior works and there are several of them, but what is the one or two that strongly related to the work? So you should only present that work because you only have 3 to 4 minutes. And then for the observation motivation is, what's the difference between this work and those prior works? So what's the motivation to motivate this work to do this research? Why not just using the prior result? So this could be included in your observation and motivations. And then for methodology overview, you can think about like, because usually the methodology, there are 4 or even 6 pages. So there will be too long if you include all of them. So try to do some summarize, for example, to point out what's the big picture of the methodology. And for example, maybe there are 3 or maybe 4 main components or designs. So try to link each component with the observation. For example, they will say like, hey, there are several observations and here are our challenges. So there are 4, for example, there are 4 like components and they propose, and they use the first component to solve the first challenge, the second component to solve the second challenge, something like that. Try to link the relationship between the observation and the methodology. And at the end, you can use like 2 minutes to show their evaluation results to briefly sum up the talk. So usually here you can see like 4 plus 3, 2, 2. So there are around 11 minutes. So here is the overview. You can use as your template to do the presentation slide. So let's talk about criteria. So first of all, so you need to make the motivation clear enough. So like organize the flow from background to rewards and to the challenges. And then if you want to make the presentation easy to follow, maybe you can think about like using some animations or maybe using some figures to easily show the flow. For example, what's the background look like and what is the challenge if we follow your background. Okay, so when you are introducing the methodology, actually you do not really need to cover all of the algorithms or like the data structures because it will take more than 3 minutes. So you can just summarize the algorithm you take from the papers. For example, what is the key idea for the algorithm? And maybe you can use maybe 3 or 4 lines of pseudocode to let me know what's the key point of this algorithm. Okay, so finally, the most important thing is do not let your presentation go over 12 minutes. Okay, so that's all for our paper presentation. And in this class, if you guys have any questions, you can just feel free to put it on the chat box, or if you want to raise your hand, it is also welcome. And just as we mentioned in the prior class, 1 question, you can get 3 points. So you can, at the maximum, you can get 9 points if you had 3 questions. Okay, so first of all, let's talk about some operating system recap. So because most of you guys already learned about operating system in the undergraduate, right? So today, let me give a very brief recap about what's the relationship between those components and give you some insights about what we will learn from these components in the following few weeks. And if you guys did not really learn or like do not really take the operating system lecture in the undergraduate, it doesn't really matter. I will try to make it easy. So let's get started. So this is our agenda today. We'll first point out the computer system organization, because I feel like operating system, even it is a software, but actually the hardware part is quite important. Because if you are going to know how operating system works, you also need to know how CPU works on like accessing memory and accessing the hardware device. So the first one is computer system organization. And then the second one is the what is operating system and Linux kernel. Okay, so you can ask yourself what is operating system and what is the relationship between operating system and Linux kernel. So in this class, we will use Linux kernel. We will follow most of the design concept of Linux kernel. So actually, we will not cover other operating system kernels, just like Windows, Solaris. We will not cover all those of them. We'll only focus on Linux. And the second one, and the third one is the structure of the operating system. What the operating system usually look like in Linux. And then in the end of these slides, I will summarize several topics that you can learn for each kind of subtopic, just like processing and interrupt, what can you learn there? And then memory management, what can you learn in this kind of subtopic? So first of all, computer organization. I think you guys are really familiar with this figure already. Just like in our computer, there are three main components, right? There are computing device, memory device, and I/O device. And people are calling them they are the three main basic components. Come to think about, I think there is a question is, so here are hardware, but what is about software? So people talk about a lot about software, right? So there are applications, and you can see now there's operating system and there are library, all those kind of things. But what is the definition of software? What kind of things can be called as a software? So here is a very brief definition I get from ChatGPT, and I think this is kind of very essential for this class. Actually, for the software in this class, we will say it is a collection of programs, data, and instructions. Although it looks so simple, it's just programs, data, instructions. But this idea can really use a lot when you are trying to know how Linux kernel runs in a CPU. And we will show you later. So first of all, because we are not using the volume architecture, so the data usually be moved from the I/O device to the memory and then to the compute unit, right? So inside our compute unit, there are usually two main things, the control units and the compute one, the ALU. Okay. So the thing is like, if after we finish our program and we are going to run our program, like using a C program, and we are going to use a compiler to compile it and then link it, and what's next? How CPU access those program looks like. So usually it looks like a sequence of instructions, right? As you learn, like after doing the assembly, and you can get a lot of instructions. So how CPU access those instructions? So usually CPU will fetch an instruction from memory, and then CPU will do a lot of things, just like decodes and executes you learn in the computer organization course. So I will not repeat it. So actually, after doing the execution, CPU usually will fetch next data or like next instruction, right? Because in our computer organization class, we say we will add a program counter by 4 bytes, for example, like that. So we can get another instructions and we can execute it, right? So come to think about instruction one, maybe this is our first program, the first line in our program, and instruction two maybe is the second line, and the instruction three is the third line, right? So CPU will fetch it one by one and then to execute it. Okay. So actually CPU will only does routine work. So what do I mean to do routine work? So without any kind of a jumper, without any kind of a go-to instruction, actually CPU will keep execute from the current one to the next one. Okay, so there's no exception. CPU will just execute next one. Okay, so CPU always do the routine things. Okay, so this is our architecture. So CPU is a kind of a hardware device, and it only does routine things, And software, like operating system, like our C program, they have a lot of program, right? There are a lot of kind of instruction there. So they can control how CPU run this program. So what is the challenge with the operating system? Let's first talk about the challenge part, and then I'll go through what is operating system. So the first of the challenge is the CPU will be solely occupied by one process if there is no operating system. So just as I mentioned, CPU starts to execute the program from the first instruction to the second and to the third, right? So if you have another, for example, you have another program, there will be put, for example, in here, then CPU will not, I mean, the program counter will not directly jump to here because there do not have any kind of context switch things. So CPU will keep executing on the same program without doing any context switching things. Okay, that means CPU will not switch to other process because there is no help from operating system. So CPU will only execute one process. So there is a fairness issues, and maybe CPU should wait for a long time when the data is in the IO device. So the second one is CPU should wait for IO device. Because for CPU, in terms of CPU doesn't really know how long should be wait for the data in the IO device, right? The reason in current system, CPU can do the context switch, that is because there is an operating system. Operating system helps to handle all this kind of context switch thing. So we can switch from one process to another process when there is a patch fault. But if there is no operating system, CPU should wait for the IO device. It cannot do anything. So the third one is the file system thing. So actually, if we do not have operating system, it means there is no, if we do not have operating system, that means we do not have file system. So CPU cannot understand what is a file. So in terms of CPU only know, hey, this is the first instruction. So we read the first instruction and we decode it, right? So instruction, for example, just like you do the add, you do the multiplication, something like that. Okay. So usually there is a no instruction code. Hey, there is a file. Can you read the file for us? Okay. So file is a concept that provided by the file system. So without file system, without operating system, CPU cannot understand file. So, sorry. So actually, what I'm going to say is, actually, if we are going to solve these challenges, there are process scheduler, memory manager, and file system. They can help on these kind of things. Okay. So coming back to operating systems. So let me first briefly talk about the rules of operating system. So what is the goal for an operating system? So you can think about operating system is a software layer. People usually call them middleware or some other kind of terms. It stands between applications and computers' hardwares. So the role of it is to coordinate and manage hardware devices, including kind of CPU, memory, and storage device. You can think about process scheduler is to manage the process and the CPU resource. And the memory manager is to manage the memory resource for different process. And file system, block layer, they're going to manage the storage device between process. So figure here shows about here are applications, operating system, and computer hardware. So the gray box here shows those kind of different applications, including the neural networks, web browser, video players. So all these kind of things we call them applications. So application, if one of the application is going to ask for the service from the hardware, for example, we are going to read a file, if we are going to get some things from memory, if we are going to use more for CPU resource, they need the help from operating system. So computer hardware device, here are several of them, you already know. So first of all, for the operating system, first rule is to make it transparency. So users do not need to worry about hardware management or contention things, right? When you are writing a program, you don't really need to care about, hey, if there are several programs that run together as a several process, then will we use other process memory or will we use other process CPU? We don't really care about that kind of things, right? We only focus on programming. So the reason is there is a help from operating system, so we can focus only on the programming. Otherwise, if there is no operating system, people need to worry about how large of memory can I use, because maybe other programmer, they're also writing a program, and maybe they are using the same like memory address that what we are using now. Then there is code contention. Okay, so if there is help from operating system, programmer can be also like it will be programmer friendly. Programmer doesn't need to care too much of hardware things. Okay, so the second one is the resource allocator. So when we talk about resource allocator, we start from the viewpoint from the hardware device. Like we're going to make our hardware device, the user becomes fairness. We don't want some process to occupy some resource for too long of time and the other maybe they feel starved. So for example, there's CPU time, their memory space, and their IO resource. So how to fairly use this kind of resource, and this is about the resource allocator. So there is also like several errors and then improper use of computers, those kind of things. For example, there's exception, there are fault things, and how to deal with this kind of fault or like exceptions things. So we have control program. So maybe you will think like control program is not that maybe important because the first two is quite important, but actually control program does take an important role here. For example, if when you are writing a user program, right? So how to make your program interact with operating system. So this is about control program because you use system code. When you are using system code, it means you are going to interact with the operating system. And system code is a part of the control program. Okay, it is kind of software exception, right? So using system code, user process can access hardware device via the help from operating systems. All right, we'll talk more about it in the following few lectures after. So because we have those rules, so it means like for each rule, maybe there should be one or two or even more components to support each kind of rule. So first of all, we talk a lot about like we need to make it fair. We need to allocate CPU time. So we have process scheduler to fairly allocate CPU resource to applications. And we have memory manager to allocate memory, to locate patches, to reclaim memory. Reclaim memory means like for some process, if the process is terminated, then how about their memory space? Is it possible to release those memory space? And if there are some fragmentation, how to do the defragmentation things. And also locate map pages. I think this is a quite interesting topic because like you guys learn about the paging things in your operating system during your undergraduate, right? So when we talk about paging, actually paging is from the concept of virtual memory things, right? But how about DRAM? I mean, DRAM is a hardware device. So what's the relationship between like DRAM and paging, right? Because you get a DRAM that maybe it is 4 GB, and then you say your patch is 4 KB. So how to map the 4 GB to 4 KB things and how to manage them. And this is how memory manager comes to deal with the problem. And then we talk about memory and CPU. So the last one is IO. So first of all, there are several kind of hardware device. IO device, for example, there are hard disk drive, there are solid state drive SSD, and there are also like CD-ROM, there are networking device there. So how to manage each IO request? So people are thinking about, for example, if there are some IO requests, we can get them from the same like hard disk drive. Is it possible to merge the requests, or how to schedule those kind of requests? So there are block IO there here to help to manage this kind of low-level things. So file system comes in as a little bit higher level than block IO layer. You can think about block IO layer is to interact with device, and file system usually we are going to interact with user, right? Because in your computer there are a lot of files. So files, the concept of files is for we human beings, not really devices. Because in the device, in a hard disk drive, in a solid state drives, they don't really care about files, right? they only care about like sector, like 512 by sector, those kind of things. So they means the hard disk drive and solid state drive, they do not really know what is a file. Okay, so this is the reason why file system is a little bit higher than the block layer, and block layer stays lower here. Okay. Okay, so I think these slides and the following few slides would be the most important things I want to let you know in a whole lecture. So first of all, what is Linux kernel? Okay, so I give a very kind of brief definition for Linux kernel. It is a process manager consists of a bunch of C and assembly code. So if you still remember, what's the definition of software? So software is just like a bunch of program that is called a software, like data, instruction, they're all called software, right? So same as Linux kernel. Linux kernel is a bunch of C and assembly code. So you guys learned about like process scheduling, there are several schedulers, and then memory manager, maybe there are body systems, there are paging, those kind of things. Actually, when you open the Linux source code, each of them, there are several hundred or thousand of C codes. So like scheduler, and there is a sketchd like .c file, and it says like, hey, here are how to implement the like FIFO or like how to implement these kind of scheduler things. So you can think about Linux kernels is a bunch of those kind of programming code. Okay. So there is a second problem is, so is Linux kernel a process? So I'll say not exactly a process. So here are several reasons to answer this. So each process should have their own virtual address space. This is the definition from our operating system, right? But Linux kernel doesn't have their own virtual address space. So let me show you an example, but this is a long story, so let's start from here. So we have a DRAM, right? So DRAM means physical address space, because DRAM is a physical device. So we will call the address on DRAM, they are all called a physical address space. Okay. So on DRAM, usually people will, the operating system will kind of slice the DRAM into several things called patch frame. So each patch frame is 4 kilobytes. So notice like here it's called patch frame, not patch, because for the physical address viewpoint, there's only patch frame, and patch is for virtual. So what is virtual? Virtual is like this. This is the first process, and this is the second process. So each process has their own virtual address space. Okay, so maybe you will be very confused about, so what's the difference between physical address space and virtual address space? So when you are writing a program, when you are writing a C program, and you will use something like memory allocation, right? MALOC function to get more kind of memory. So actually, when you deal with those kind of memory, they are all on the virtual address space, right? Because you don't really care about this memory is on which area of DRAM, and you don't really care about if there are 10 users, if there are 100 programs that run simultaneously on the DRAM, which process can use which DRAM slot, right? So this is because for Linux system, we have virtual address. So each process only need to care about their virtual address. So in the 32-bit systems, people usually say the virtual address there are 4 gigabytes. So you can only use 4 gigabytes, but now there are 64 bits, so you have a lot to use. But what I'm going to say is, come to think about, this is a first process. It means like you can think about this is first program, and then this is the second program. So each program has their own virtual address space, right? And it is possible two virtual address space can share the same physical address space. Okay, but how to do this mapping, and that is about, sorry. So how to do this mapping, this is about the patch table. So patch table will stand here and then to do the mapping between the virtual to physical. Okay. So because there is virtual address space, so you guys programmers don't need to care more about physical things. So this is a good thing that virtual address space can let the programmer get. So there is another good thing for using the virtual address is like currently you guys know a lot about the large language model things, right? Large language model, there are super large model size, the KVK size is super large. So it is hard to put the whole model in a memory. Then how do we run this kind of like I mean the processing is so large of the memory space, but we don't have that kind of large space. So usually we will have the storage device as a swap device, right? It means like you can think about just like the extension of the DRAM because we don't have that much of DRAM. So why not use part of the storage device as the extension of DRAM? And this is called a swap space. So when we are going to move the data from the memory to the storage device, we call it swap. Okay, so if each time we do the swapping, the programmer should come into to deal with its virtual address and physical address. It takes a lot of overhead, right? Because swapping, I mean, the good thing of swapping is it is transparent to user. It is transparent to the programmer. Programmer doesn't need to know what is swapping, right? Because what we are going to do, what the system is going to do is to make these swapping things transparent enough, and we can do a memory extension like easily. We don't need to bother the programmer. Programmer doesn't need to care about we have enough or we don't have enough memory. Okay, so like this, if we can modify the patch table, the mapping from here to here, then actually we can finish the things. What I mean finish is when you are running a program, actually, when the program is going to access the data from these locations, patch table can redirect it to a correct position in the physical address, right? Because originally the data is here, but because we do the swap, so when the data is moved to the storage device, and using this kind of patch table kind of, actually we do not really change the location in the patch table. We only set a non-present bit here, and there are some function in the Linux kernel that can help to find out where is the location in the storage device. Okay, so for those kind of things, they are included in the operating system. So programmer doesn't need to know these kind of things. Programmer only need to know, okay, my data is here, so I'm going to get the data from this virtual address. All right. So if you take a deeper look into this kind of virtual address space, actually virtual address space look like this. So there are lower several gigabits. So if there is a 32-bit system, like here is a 3 gigabit and here is a 3 gigabyte and here is a 1 gigabyte. So actually, you can see user process can only use a 3 gigabyte and the top address space, they are all for the kernel. So for all different kind of process, the first, the topmost 1 gigabyte, they are all allocated for the Linux kernel. So this is the reason why I say it doesn't have their own virtual address space, because Linux kernel share their virtual address space with their user process. Okay, so originally this is the address space for the user process, but for each user process, they will allocate 1 gigabyte for the Linux kernel. Okay. So you can think about like this. The user program and process data, they are all stored in this kind of virtual address space for each process. So for example, this is process 2 and process B. So this user program is user program B and process data related to the process B, right? But for the kernel address space, what kind of data is in the kernel address space? For example, the code for the scheduler, right? The memory manager's code, and then the file system code. All those kind of things, they are all in this area. So when you are running a user process, and then you need a service from, and you need a service from the operating system like Linux, you do not really need to switch to other process, right? Because you are in the same virtual address space. So for CPU just only need to move to access the other, the data on the on the topmost virtual address space map it to, then we can access them. So come to think about, if for a Linux kernel, it is a process. I mean, if there is a process called Linux kernel, then when a user process needs the service from Linux kernel, then it needs to do the context switch, right? Because when we are going to access all the process in the same CPU, we need to first store the process context for the prior process, and then we can switch to another process. And it takes a lot of overhead here. If Linux kernel is a process, and each time you want to do something like memory manager, process scheduling things, you need to frequently do the context switch from one process to the Linux kernel process, and you will take super heavy overhead. So this is the key reason why for the Linux kernel, they share the virtual address space with all the process. So this is the reason why it's like Linux kernel is not really a process, because it share most of the it share the virtual address space with others. Okay. So here are some descriptions here. So kernel runs as, okay. So kernel runs as part of a user process. So there is a specific part of all process virtual address space pointing to the same physical address storing kernel code. Actually, this is just a brief description, and we'll come back maybe in the later few weeks. We'll come back to deeply introduce about what does this sentence mean and what's the mapping, how to map like the Linux kernel code to all the process. Okay, so currently there's one thing to let you know is, but how does CPU know we are not executing the user process or the kernel? So in the CPU, usually there is a like bit. The bit is called mode bit. And the mode bit, for example, if it is in bit 0, and it means CPU is in the user mode. And if the bit becomes bit 1, and it will becomes in the kernel mode. Okay, this is just a simple way to let you know. Actually, it is not really a bit, because in the CPU there are several layers of the different privilege here. But simply, let's make it simple. Is you can think about when CPU in the user mode, CPU can access the data in the virtual address for the user. But when there is a patch fault and CPU switch into a kernel mode, CPU can access the data in the kernel address space, which means CPU is now running the operating system. Okay, so because there is a patch fault, so usually when we are going to know what kind of patch fault it is and what is the following that we are going to do, we need a thing called patch fault handler. So patch fault handler is also part of an operating system. So when we are going to execute this kind of operating system code, CPU need to switch their mode and then to execute it. So the thing is, actually, they are all the same CPU. I mean, this is the same CPU. The only difference is it switches mode from user mode to kernel mode, or kernel mode back to the user mode. And the mode is just like a bit. So the bit is going to let the CPU know, hey, I'm now in the user mode or in the kernel mode. In the kernel mode, I can access the kernel virtual address. But if in the user mode, I cannot access the kernel virtual address. So this is just the way like how CPU supports this kind of structure. Oh, one thing to let you know, actually, most of the kind of architectural design of CPU, they are really related to the operating system design. And one of the reasons is because when you are going to design an operating system, actually there are a lot of resources in the CPU, for example, register, those kind of things we need to use. So this is also one of the reasons why actually Intel and Microsoft, there are two very important like contributor for the Linux kernel, because they contribute a lot in Linux kernel. Then for example, like Intel, they can have their own CPU design, so they can support their own kernel function, like these kind of things. Okay. So here is the note here. So actually, CPU switch to kernel mode to access the operating system code, but CPU doesn't need to switch the context. Oh, here is a key thing. Actually, when CPU switch the mode, actually this is not called the context switch. This is only the mode switching, because for this one, CPU only switch the bit. And then, slightly do this kind of register copy. It doesn't really like the process context switch, because the process context switch, that is the things you learn in the operating system in the undergraduate. You need to store a lot of data related to this process. You need to store the virtual address space. You need to store the patch table things. But now here, you don't really need to store those kind of things. The thing the thing CPU needs to do here is just to switch the bit. So it doesn't have too much of overhead here. It is fast. So this is the reason why this kernel want to design like this way, not really like a process. If it is a process, then this will not be only mode switching. It will be the real context switch. Okay. So here is a very tiny kind of diagram or like example to let you know what's happening here. So come to think about, there is a submarine, and this submarine represents the process A, right? So when process A is running, it is on a user mode. So it means like this submarine is on the is above the water surface. So it means like the process A, when it is kind of driving here, it is in the user mode. So when this process A needs the service from the operating system, process A will dive into the water. And if the process A is in the water, or like you can think about if the CPU is in the kernel mode, actually this is still the same submarine, right? So user mode or kernel mode, actually this is the same submarine. It means like system doesn't need to change CPU. It's still the same CPU. The only different thing is the mode. It's just like the only different thing is the bit in the CPU. It changed from 0 or 1 or 1 or 0. So when the CPU is in a user mode like this, it means CPU is now running the user A data, like in here. Here is the data for user A, the location. And when CPU now dive into the kernel mode, so it's still process A, but actually CPU now can access the data in the kernel address space, right? But no matter in the kernel address space or user address space, they are all belonging to user process A. Okay, so this is just a total example to let you know, actually, there is no switching between CPU, they're on the same CPU, and for each process, if you change the submarine to process B, actually, they still share the same kernel, because no matter which process it is, they run the same process scheduler. Okay, but there are some tricky way here to say like how do they share the kernel code, but I will not explain here. I will explain later when we are in the kind of lecture, when we're introducing this. Okay, so actually, when you are using the Linux, actually you will see there are some kernel process. There are really kernel process, and actually there are like some daemon things. What I mean for daemon is, for example, there is kind of monitor. There are some monitor process that are going to monitor the system usage. For example, the like CPU usage or like the memory usage, and they do. There are truly a kernel process, but there are slightly difference, because for example, you will not see like the process scheduler is running here. Okay, so this is a little bit tricky, because truly part of the kernel, they are truly process, but I would say like most of the things you learn in the undergraduate things, for example, file system, memory manager, process scheduler, they are not really process. Okay, so just to make it clear, because when you are using the Linux, actually you will see some daemon like KSOP, those kind of daemon things. Actually, they are going to monitor your system usage. Okay. Okay, so let me move on to our next question. So when do CPU run kernel? Okay, so this is also a very brief definition here. CPU runs the kernel when some special events are triggered. Otherwise, it runs user programs or stays idle. So here are several different events. First of all, it is called hardware interrupts. So hardware interrupts including timer interrupt, IO interrupt. For example, when you type on the keyboard, when there is a hardware device, they send a signal to the CPU. They are all called hardware interrupts. Okay, so for example, when there is a CPU scheduler, right, and we are going to switch, we are going to switch from one process to another process because the prior process used too much of the time, then we need a timer interrupt inside the CPU. Because a timer interrupt can barely count how long each process takes. And then if you use too much of time, timer interrupt will interrupt the CPU. So we can run those kind of CPU scheduler things. Okay. So there's another thing is called software generated interrupt. So there are traps, exceptions, including system call and patch fault. So here's a question for you, just like why we needed this kind of spatial events here. So the reason is, if you still remember, we say CPU will only do routine work, right? CPU will only run instruction next to the prior one. So coming back to our first patch here, if instruction 1, 2, and 3, they belong to the same process, then they will not be operating system, right? Because this is all related to process A's code. And process A written by user A, for example. So they will not be the operating system. In this case, if we are going to run operating systems, the only way is to interrupt CPU, right? If we don't interrupt CPU will keep execute instruction 4, 5, 6, and they are all belonging to the same user process. So there is no way for us to run operating system. So we need some ways to interrupt CPU. We need some ways to stop CPU, to let CPU to run something else, like operating system. So this is the reason why we say there are two ways, hardware and software. So hardware means like, hey, for example, memory or like IO device, we can interrupt CPU. So CPU can stop here and then to jump to other place. The program counter will jump to other place to execute the instruction. So quick example here. I think it's this one. 1 minute. Okay, so just focus on the figure on the right-hand side. Where is my mouse? Okay. So actually you can think about here, first instruction, second instruction, third instruction, fifth instruction, right? There are sequence of instructions. So when CPU now is executing the user program now here, if there is no spatial events, if there is no hardware or software events, CPU will just keep executing them. CPU will not do anything else. But now, for example, if the data is not in the memory, the data is in a storage device, then you are so familiar with it because people will call it, a CPU will call it a patch fault, right? But even there is a patch fault, CPU still don't know, where to execute the patch fault handler because patch fault handler is here. So in the perspective of CPU can only execute here, right? So the thing is, because there is an event trigger called patch fault, so inside the CPU, there is a register to let CPU know, hey, if you get a patch fault, please redirect your program counter to some spatial physical address. Okay. So there is a patch fault. So inside CPU, there is a register. The register record, the patch fault address is in here, right? So if there is a patch fault, CPU will switch from the program counter will be switched from here to here. Then CPU will start to execute it from here, and then it still go for the sequential way to execute the whole patch fault handler. So this is the way CPU run the operating system. Okay, so there's an event, then CPU can switch to other place. If there is no event, then CPU will just stick on the original user process. Okay. So let's. So actually, each of them will give you a deep dive in the following lecture. For example, how does interrupt occurs? Because it is there is a keyboard, right? So how keyboard can send a signal to the CPU, right? Then how CPU can know there is a signal from keyboard, and what kind of interrupt handler can CPU run, right? How CPU run this interrupt handler, and then how CPU runs the operating system. So they will be in the following course, and then also the system call and the patchable things. I mean, when we are going to read a file, when we are going to write a file, and we need system call, right? But what is the CPU looks like when CPU gets a when CPU runs a system call? What will CPU do next? So we'll introduce all these kind of things, and also you will get some hands-on call part, I think. Okay, so coming back to our toy example here. So the same thing, we have a submarine, it means process A. So process A is now running in the user space. So user space, it means CPU is in the user mode and CPU now is running the program related to this process A, right? Okay, so when process A needs to do some like read file, write file, or some other system code stuff, then the CPU will switch to the kernel mode because CPU needs to execute this kind of system call handler. And system call handler is part of operating system. So CPU should switch to kernel mode to execute it. Okay, so you can think about the system doesn't switch to CPU. It's still on the same submarine. So we are still on the same process and the same CPU. And after executing the system call handler, for example, the read things, and the CPU will switch back to the user mode, so the process A can runs normally. Okay, but now if there is a timer interrupt means like process A runs too much of time. We need to switch to other process, right? So the same thing, CPU switch to kernel mode and to execute scheduler. The thing is, because we need to do context switch, so we switch in the other process, right? This is not process A. We switch in, for example, process B. Okay, so after executing the scheduler, process B goes back to its normal execution, then CPU switch back to user mode. So you can see like now we have a different process B. Okay, so this is how the user process execution and the relationship between the operating systems. Okay. Oh, and there's another thing. So just like if there's IO interrupt, then there's the same thing because we are not on the process B. So CPU will go into the kernel mode to execute the IO scheduler. Okay. So this is the process of the how execution of the kernel. Okay. So let's put it all together. So here is a high-level overview here. So in the user space, there is applications. So application include like TensorFlow, Hadoop database, and like PyTorch, all those kind of things. They're all in the application. So below the applications, there is libraries. So including C, C++ library, and like maybe Python, there is an interpreter, all those kind of things. So they are all below the application. So library is a good thing because it helps you to abstract the complexity of the operating system. With using library, you don't really care about like how to code the system code, right? Because in your core, you only need to know, hey, I'm going to do the memory allocation, and you can just check the spec and then you can write the code. You don't really need to know about like which kind of physical address that you are going to allocate, and then if there is some contention across different kind of process things. So this is what library is. And then there's a system call glue between the C library and then the kernel space. So for the kernel space, there is a core kernel, and there's device driver, the hardware. Okay. So inside the core kernel, there are several things. The first one is process manager, and the second one is memory manager, just like at the right-hand side part. So this is just the core kernel part. Then for the memory manager and process manager, they will work with the files, the I/O part. So the I/O part including the virtual file systems, networking, device drivers, things. So I think most of the block here, I mean in the kernel space, not in the user space. Most of the in the kernel space we'll cover in this lecture. Okay, so I think we can tag a 10 and then we'll come back later.